The 75-day thermal hurdle. A single 12,000-pound radiator is the only thing currently preventing the Dream Chaser from melting its own internal computers during its upcoming 75-day stay at the space station. With the successful completion of high-intensity acoustic testing on April 15th, Aerospace has validated the architecture that will finally break the 2-week endurance ceiling of orbital spaceplanes. This is the end of the cargo bottleneck. But to understand why this module is a requirement rather than an upgrade, we have to look at the thermal trap that killed the space shuttle's long-term utility. The physics of the thermal trap. Space is not cold. It is a thermos. For a vehicle packed with electronics and crew, the primary challenge is not keeping warm, but dumping heat into a vacuum that refuses to conduct it away. The space shuttle could only stay docked for about 2 weeks because its radiators were mounted on the inside of its massive cargo bay doors. To stay cool, it had to keep those doors wide open, making it a sprawling and vulnerable target that could never integrate into long-term station operations. Dream Chaser solves this by offloading the entire thermal management system to the Shooting Star module. This externalized heat sink allows the main ship to stay sealed and protected, finally bypassing the thermal wall of orbital endurance. The Sacrificial cooling architecture. The Shooting Star is effectively a 5-meter-long active radiator wrapped in solar panels and cargo racks. It utilizes a high surface area skin made of extruded aluminum panels with integral coolant tubing that rejects heat even in direct sunlight. A 50-50 mix of propylene glycol and water carries energy away from the avionics and into these external vanes, where it is radiated into the blackness of space as infrared energy. This system can reject over 1,100 watts of heat at peak operation. By placing this entire cooling rig on a disposable module, engineers avoided the weight and complexity of building massive, deployable wings into the reusable airframe itself. This allows the plane to focus on flight, while the module handles the metabolic load of the mission. This separation is exactly how the system manages the station's most pressing physical requirement, the waste problem. The One-Way Incinerator. Endurance is not just about heat, it is about what you leave behind. The International Space Station produces thousands of pounds of trash that traditional return vehicles simply cannot handle. The Shooting Star is designed to haul 8,500 pounds of this waste away and incinerate it during re-entry. It is the only system that decouples the return of high-value science from the disposal of low-value station refuse. And this shift in utility reveals a fundamental pivot in how we design orbital hardware. The logistics shift. The success of the Shooting Star module proves that the future of space commerce depends on modularity rather than all-in-one reusability. By separating the cooling and disposal functions from the primary airframe, Aerospace has created a template for persistent orbital logistics that addresses the two biggest mission killers: heat soak and waste accumulation. This shift moves the industry away from the expensive, integrated architecture of the past and toward a terminal-based model, where the high-value vehicle stays clean while the Sacrificial module does the heavy lifting. This approach means the same Dream Chaser can be refitted for entirely different mission profiles simply by swapping its tail, reducing the cost of mission-specific engineering to nearly zero for commercial operators. This strategy forces every other competitor in the cargo market to explain why they are still launching all their capabilities in a single, non-modular hull. The next critical indicator of this shift is the flight demonstration scheduled for late 2026, which will be the first real-world test of the module's ability to maintain these thermal margins over an extended orbital duration. Subscribe for more.